when we're considering continuity, really we're thinking about when we draw a function, do we have to lift our pencil? So in the case of this sine function here, no, we don't have to lift our pencil. We can continuously draw that function from the beginning of the domain to the end of the domain. So within that domain, that function is continuous. Same with the second function, which is just a line. Third function, which sort of looks cubic. And fourth function. Now, we got this little point down here, but still, in order to continue drawing it, I do not have to lift my pencil. So we would say those four functions are continuous. So notice for these examples here, if I start drawing them with my pencil, oops, here like the asymptote one, I'm going to have to lift my pencil in order to draw that whole function. Here, if I'm drawing the function like this, I'm going to have to stop at this hole and draw this one point up here and then continue for the rest of the function. And here, for this one, it looks like a cubic, I'm going to have to stop, lift my pencil, and sort of jump over this little hole here. And lastly, this one here, I'm obviously going to have to jump up here in order to draw the function. So all of these are discontinuities, or discontinuous functions, I should say. So let's take a closer look at this first function, the function with the asymptote. Now, so what makes this function have an asymptote? Let's start off by looking at the equation of this function. We know the parent function is going to be 1 over x, because that's what it looks like. And it looks like that 1 over x has been shifted 3 to the right, because the asymptote has been shifted 3 to the right. So we can sort of guess here, just by looking at it, that the equation is going to probably be 1 over x minus 3, or something close to that. Okay? Now, what about this equation tells us it's going to have an asymptote? Well, obviously, the denominator cannot equal 3, right? Because if it does, this function is undefined. So x cannot equal 3. And that tells us it has an asymptote, right? One other condition, so wherever the denominator equals 0, actually, we'll just summarize this here, right? So denominator, wherever the denominator equals 0, that's where we're going to have an asymptote. And this actually only happens if the degree of the denominator is bigger than the degree of the numerator, right? Just like this case. So degree of denominator, in this case it's a linear function in the denominator. Degree of denominator is greater than the degree of the numerator. Okay? Now let's look at these second functions. This first function here, we actually call this type of discontinuity a dislocation, because it's like we took this point here and we pushed it up there. Now, really the only way this is going to happen is with a piecewise function. So keep an eye when you have a piecewise function. If there's one point that's in a different location, then that maybe will tell us that there's a asymptote there. For example, this is like a quadratic. It looks like a quadratic. So it looks like it's a quadratic everywhere except for at 2, and at 2 the function exists at 1.5. This function down here has what's called a hole. So the function doesn't exist at that point, and it's not like it's moved anywhere else. It has a hole. And we know this happens when you have a function. Now this isn't going to be the function here, but this is just an example. Say we had a function like this, f of x equals x plus 2, x plus 3, all over x plus 2. So we have this function here, and if you look at it, it's going to simplify, right? So x plus 2 and x plus 2 are going to cancel each other out. So if we think about the restrictions on this function, it looks like the final function is just f of x equals x plus 3. But that's not exactly true, and that's just a line, right, with no restrictions. But that's not exactly true, because the original function had an x plus 2 in the denominator, which tells us x actually cannot, in this case, equal negative 2. So in this case, we would have the equation of a line based on that, but at x equals negative 2, there would be a hole. So essentially we get holes whenever we have factors that are going to cancel out of the denominator. And holes are at the location that would make that function undefined. The last type of discontinuity is a jump discontinuity. And these usually only really happen with a piecewise function. So we have a linear function here and a linear function here. And obviously those are two different lines that don't exactly match up. So we would say this happens because of a piecewise function. And the other case you might see something like this is if you have an absolute value function. Okay? So now looking at the definition of continuity. Before we said continuity is basically do you have to lift your pencil or not. More mathematically accurate, we can say a function is continuous if two conditions are satisfied. If the point that's in question is on the line, so if A is defined at that point, and B, the second condition, is if the limit exists at that point. So looking at the first one here, we see that the function is actually not defined at 3. Also, the limit does not exist at 3. So it fails both conditions basically at this point, so we would say the function is discontinuous. Looking at the second question. Now, if we look at point 2, does the limit exist at 2, at x equals 2? Well, yes, it does, because the function approaches from the left and the right-hand side. And also, the function exists at that point too. But the problem with this case is that what the limit approaches and what the function exists at are not equal to each other. So actually, the function's value at that point and the limit need to be equal to each other. And in this case, they're not. Here, for the third one, we have the limit existing here again, right? From the left and from the right, that function, the limit of the function as x approaches 2 exists, but the function does not exist at that point, so we would say it's discontinuous. And lastly, for the jump discontinuity, the limit from the left and the limit from the right are different. So that means that this limit does not exist, even though the function exists. So we would say it's discontinuous because of that reason. So these are reasons we can use to prove or disprove whether a function is continuous at a point. So let's try some examples now. These questions ask us to determine if the function is continuous at the given point, and if not, what type of discontinuity is present. So the first question is a piecewise function. And for piecewise functions, you should always sketch the piecewise function just to see what happens at that x equals -1. So our first part of the function is a quadratic, and it's the parent function of a quadratic that's been shifted down by 3. So if I sort of draw these marks here, and what's going on is between -1 and infinity or whatever, we have this function existing down here. So it's been shifted down there, and we know a quadratic is going to look something like that. Okay? Doesn't really matter what's happening over here because we're really concerned with what happens at -1. If you remember your step pattern at -3, 0, that's where the function is going to start. Over 1, up 1, that's the next place the function is going to be. So at -1, the function exists at -2, it looks like. Let's look at our second part, which is a linear function, x minus 1. And what that looks like, it's a line that's been shifted down 1, or has a y-intercept of 1. So it would start here. It would start up here, but it doesn't exist at -1. So really, if you think about it, at -1, that function is going to exist at -2. So it's actually right on top of where this one is, and it's going to go downwards like that, because that's a positive slope. So this is our piecewise function. Notice how, for both functions, they meet at this point. So is it continuous? And the answer is yes, because the two pieces of the piecewise function meet at the same point, -1, -2, so this is continuous. So next function, 3x to the power 4 minus 2x plus 5. Is this continuous at x equals 4? Well, what type of function is this? It's polynomial. And we know for a polynomial function, our domain is always going to be x is an element of real numbers. So that means that this is going to be continuous everywhere. So it is going to be continuous at x equals 4. At x equals 4. Looking at our next example here, x plus 5 over x minus 2 at x equals 2. One thing we could always do, by the way, for these, if you want to check your work as you go, is plug the function into Desmos, and that'll make it pretty obvious. But for this function here, what happens to the function at x equals 2? Well, if we look, this function is undefined at x equals 2, right? We're going to have a 0 in the denominator, which means we're dividing by 0, which means the function is undefined at x equals 2. And if you remember from our previous page, when we have a discontinuity like this in our final function, we can't really simplify this at all or cancel anything out. What type of discontinuity is present? And the answer is that it is a asymptote. So we have a vertical asymptote. Actually, I should put that. We have a vertical asymptote at x equals 2. Okay? Just by looking at the equation. Our next function is another piecewise function, and I'm always going to say sketch the piecewise function. So the top part of the piecewise function, x squared minus 4 over x plus 2, that's a little bit complicated to sketch, but what we can do is we can try to simplify that thing. So I'm just off to the side here. If I look at what's in the numerator up here, I can see that that top thing can be factored. So the first part of this can be factored as x minus 2, x plus 2. It's a difference of squares over x plus 2. And we can see that those two things are going to cancel out when we do that. So basically this top part of the function up here, that's just going to equal x minus 2. And the condition there is that x cannot equal 2 because we would be dividing by 0, or negative 2, because that would be dividing by 0. But that condition is already given to us in the piecewise function, so we don't need to worry about that. So basically the graph of this thing is going to look like x minus 2, which is a line that has a y-intercept of negative 2. So I'm just going to draw it like that. I should really put these marks here. And at x equals negative 2, we're going to have a hole, right? So if negative 2 is going to be somewhere down here, so if this is negative 1, negative 2, it's going to be somewhere down here, we're going to have a hole. And it looks like that hole is going to be at negative 2, negative 4. Now let's look at our other part of the piecewise function. It says if the function is negative 2, the function is equal to negative 4. So looking at that, negative 2, negative 4, is filled in because at negative 2, the function is negative 4. So this piecewise function sort of takes care of the hole. It fills in the hole for us. So is this function continuous? And the answer is yes, it is continuous. This is one way we can get around a function like this. If it does have a hole, we can fill in that hole manually with a second part of a piecewise function. Here we have another piecewise function, so we're going to graph it. But again, the top function is a little bit tricky to graph, so let's try simplifying it first. If we look up here, this is a polynomial or a trinomial that can easily be factored, right, using product and sum. Two numbers that multiply to get negative 2, add to get negative 1, and I think those numbers are going to be x minus 2, x plus 1, all over x minus 2. And what happens is those two cancel out. So again, we have a condition here that x cannot equal 2, but that condition is taken care in the piecewise function as the condition for the piecewise function. So basically what we're left with is this function here simplifies to x plus 1 where x cannot equal 2. So again, let's sketch this part of the graph. X plus 1 is just a a line with a y-intercept of 1. So that's just going to look like that. And it's going to have a hole at x equals 2. I didn't draw these lines very well. So at x equals 2, we are going to have a hole. So if you think about where that is, that's at x equals 2, and we're just going up 1 each time from here, right, because the slope is 1. So this hole is going to exist at 3. So there we go, that's the first part. Now if we look at the second part of the piecewise function, the function equals 2 if x equals 2. So we can graph that right there, just underneath the hole. So is the function continuous? Well, no, because the hole is there, and the function has basically been dislocated down there. So we would say discontinuous, and it is a dislocation of that point. Lastly, we have an equation or a question, and it says determine k so that mx is continuous. Mx is a piecewise function, and the first piece of that piecewise function, notice how it's just a linear function, and it exists everywhere x does not equal 4. So we can always start by graphing this. And the function looks like 9x minus 1. So it's a very steep line that crosses at -1. Something like that. Okay? And we know it does not exist at 4. So if we make this 4 right here, so it does not exist there at 4. So we want to basically determine how to make this function continuous. So essentially, if you want to think about it, we want to fill in that hole. So we have this second part of the function here in order to do that. So how are we going to do that? Well, let's first try to find out where that hole is, right? So if you think about it, the hole is going to exist at that function 9x minus 1 wherever that function would exist, right? So if we find that function 9 times 4 minus 1, that's going to tell us the function would exist at 35, right? So that point here is at 35. Even though there's a hole there, if the function did exist at 4, that's where it would be. So essentially, we need to make that second equation equal 35, right? Because if that second equation equals 35, it's going to fill in that hole. So I'm just going to set that as second equation. 35 is equal to 3x plus k. And then we have to solve this equation. And now, which x value are we trying to solve for? Well, this occurs also where x equals 4. So 35 equals 3 times 4 plus k. We can solve that equation. So go for it now. You can pause the video if you want. Simple solving. K turns out to be 23. So if k equals 23, that second part of the function here, 3 times 4 plus 23, is going to give us 35 and is basically going to fill in that hole. So there's our answer. K equals 23.